Hello everyone, welcome back to my YouTube channel. So earlier we have derived the Bragg's equation, that is n lambda is equals to 2d sine theta. Now we move on to application of Bragg's equation to find out the types of crystal structures. Now this Bragg's equation as written is n lambda is equals to 2d sine theta, where this n is the order of the reflection. Lambda is the wavelength of incident X-ray. D is the interplanar spacing, whereas this theta is the Bragg's angle. Okay, so this is for a particular HKL or the Miller indices of a plane. So we should write n lambda, suppose copper K alpha, is equals to 2d HKL sine theta HKL Bragg. So this Bragg's equation is actually a negative statement. How? So if not satisfied, no reflection can occur. If this is not satisfied, no reflection occurs. Okay, no reflection. But if satisfied, if it is satisfied, reflection may occur. It is not necessary the reflection will occur. It may or may not occur. This is to be noted that it may occur. So we see that interplanar spacing occurs in the Bragg's equation, but the interatomic spacing is not there. Okay. So suppose for first order reflection, for first order reflection from 110, okay, for a cubic crystal. Okay, so D is equals to D110 is A by h square plus k square plus L square, where A is the lattice parameter. So A by root 2. Okay, so and n equals to 1. So, and if we use copper K alpha radiations, this implies lambda will be 1.54 angstrom. So, n lambda is equals to 2d sine theta. This is 1 into 1.54 into 10 to the power minus 10 is equals to 2 into a by root 2 sine theta. So, from the XRD data we can get this theta value, so hence we can calculate this lattice parameter A. So, this is how we use Bragg's equation. Now, some important points. So, presence of additional atoms in the unit cell at lattice points or as a part of the motif can alter the intensities of the reflection. Okay, so the intensity of the reflection depends upon the number of atoms or the location of atoms. Okay, so position of reflections, they gives us the lattice type, whereas intensity gives us motif information. Okay, so it is clearly defined that lattice information is given by the position and motif information is given by the intensity. Now, but Bragg's equation tells us only about this position. This is given by Bragg's equation. Now, how to find the intensity? So, there are certain ways to have the intensity calculations. Okay. So, scattering by an atom can be understood in 3 steps. First is scattering by an electron, that is given by the polarization factor. Second is scattering by the atom. This is called the atomic scattering factor. So, we have a relation for atomic scattering factor, that is given as uh, I forgot that, let me recall. So, yeah, that is given as F is equals to amplitude of the wave scattered by an atom upon amplitude of the wave scattered by an electron. So, it is this particular ratio. So, now next that we have is the structure factor or scattering by unit cell, which is called structure factor, capital F. So, capital F is amplitude of wave scattered by all atoms in the unit cell, amplitude of wave scattered by all atoms in unit cell divided by amplitude of wave scattered by an electron. Alright. So, after many derivations, we have a formula for structure factor which says capital F is equals to summation from j equals to 1 to n atomic scattering factor into e to the power iota 2 pi hx plus ky plus lz. This is j. with j as subscripts. Alright, so for scattering by an unit cell, certain points are considered, and these assumptions are: the scattering is coherent, next, unit cell is representative of the crystal structure, third is scattered waves from various atoms in the unit cell interfere to create the diffraction pattern. They interfere, or rather constructively interfere, to create the diffraction pattern. Alright, so these are considered while deriving this formula for structure factor calculations. Now, this formula helps us in giving the selection rules for the reflections that are present or absent in a particular type of lattice or crystal. Okay. Now, let us see some examples for structure factor calculations. Okay. So, let us start with simple cubic structure. Okay. So, for a simple cubic, the atom, it has only one atom, and the atom is at 0, 0, 0 and the equivalent position. So, FHKL is equals to FE, since we have only one atom, 2 pi Hx plus Ky plus Lz. So, F is given by all are 0. So, F e to the power 0. So, alright. So, we see no matter what HKL is, all reflections are present. Okay. So, reflections are present for all combinations of HKL values. Now, similarly, we move to body-centered atom. Sorry, body-centered structures. So, we move to body-centered. So, in body-centered, you have two atoms. So, number of atoms is 2. So, atom positions are 0, 0, 0 and half, half, half. So, let us go for structure factor calculation, which is summation j equals to 1 to n, where n is the number of atoms, f e I 2 pi h x j plus k y j plus L Z j. So, we get f is equals to small f. So, first, let us put this point 0, 0, 0. So, we get f to the power 0, e to the power 0 plus f e I 2 pi h by 2 plus k by 2 plus L by 2. So, we get capital F is equals to small f plus f e to the power I pi h plus k plus L. So we get f 1 plus e iota pi h plus k plus L. So we know if h plus k plus L is even, now we have two choices. If h plus k plus L is even, or so we will have then this is equals to 1. Okay, since this is even, it will be like 2 pi or 4 pi, which will be 1. So since this will be expanded as, suppose if it is 2 pi, if this is 2, if h plus k plus L is 2, so it will be e to the power 2 pi iota, which is cos 2 pi plus iota sin 2 pi, which is 1. So we get f is equals to 2f, or if h plus k plus L is odd, then e to the power iota pi h plus k plus L will be minus 1. So capital F will be effectively 0. So here we do not get any peaks. Since intensity is 0 and I is equals to F square or directly proportional, sorry, I is directly proportional to F square, and since F is 0, so intensity will be 0, so we do not get any peaks. But here I is directly proportional to F square and F square is equals to 4F square, so we get peaks when H plus K plus L is even. Okay, so this is for body centered. Now for face centered cubic. So face centered cubic actually has 4 atoms per unit cell, and atom positions are 0, 0, 0, half, half, 0, half, 0, half, and 0, half, half. So let us calculate the structure factor. For this, we get capital F is equals to small f, and then within the summation we go like e to the power I 2 pi 0 plus e to the power I 2 pi h by 2 plus k by 2 plus 0 plus e to the power I 2 pi h by 2 plus 0 plus L by 2 and plus e to the power iota 2 pi 0 plus k by 2 plus L by 2. So we get capital F is equals to small f, this is 1, plus e to the power iota pi h plus k plus e to the power iota pi k plus L plus e to the power iota pi L plus k. Sorry, this is h plus L and plus k. This is what we get, and this should be a real number. So if now we have two choices, if all h comma k comma L are either even or odd. Okay, so we get, when they are either all even or odd, then sum of two of them will always be even. So this implies capital F is equals to 4F. Now if H, K, L are mixed, that is they can be either even or odd, then F is equals to 0. So here F square is equals to 16F square and F square is equals to 0. So in this case reflections go missing. Okay, so for example, for a mixed index, if we see that is 2 even or odd, so suppose we have H, K, HKL of 1, 1, 2. These are 2 odd and 1 even. So capital F will be small f 1 plus, this is e to the power 2 pi iota, then k plus L will be, sorry, H plus L will be e to the power 3 pi iota plus e to the power 3 pi iota. So this becomes capital F equals to small f 1 plus 1 plus minus 1 plus minus 1. So this becomes 0. Okay. So this is the structure factor calculation for FCC. So let us summarize which reflections are present and which are absent in general lattices. So we have a Bravais lattice type, then we have reflections which may be present, then reflections that are necessarily absent. Okay. So as we have derived for simple cubic, all may be present. So necessarily absent is none. Then we have body centered. Here H plus K plus L is equals to even can be present and H plus K plus L is equals to odd is necessarily absent. Then we have face centered cubic. So H, K and L unmixed. That is either all odd or even, and that are necessarily absent are H, K and L mixed. Okay, and then we have end centered where H and K unmixed, they may be present, whereas H and K mixed is necessarily absent, that is one odd or one even. Okay, and then we have one more, that is diamond cubic. Okay, so for this we have criteria 1, that is H, K, L are all odd, and then criteria 2, all even, and these should be satisfied simultaneously. H plus K plus L divisible by 4. These are the ones that are allowed. Okay. So this was to summarize what type of reflections are present or can be present. Okay, so now for h square plus k square plus L square values in simple cubic or FCC, BCC and diamond cubic. So 1, 2, 3, 4, 5, 6. So h square plus k square plus L square, take this can never be 7. So 8, 9, 10, 11, 12, 13, 14 and so on. So in simple cubic, since all are present, so you can say this is 100, this is 110, 111, 200, 210, 211, 220, 221 or 300. This is 310, 311 and this is 222. This is 320, 321 and so on and so forth. But in FCC you have H plus K plus L unmixed. So unmixed is this, then 220, then 311, 222. Okay. And for BCC you have their sum should be even. So 110, 200, 211, 22. Sorry, this is sorry not 21. Yeah, 211. Then 220, then 310, triple two, 321. These are for BCC. Then for diamond cubic we have either all are odd or they are all are even and their sum should be divisible by 4. So all are odd. Now this all are even but it is not divisible by 4, so this is not present. So let me write all odd one and this one is all odd. Now all even, this is 220 and it is divisible by 4 as well. Okay, so we get a series of h square plus k square plus L square values for FCC, BCC, diamond cubic and simple cubic. Now this can be used to determine the crystal structure, which we'll see in the next lecture. Thank you.